Hello and welcome. This is our lecture video for September 14th through the 15th. We're going to be talking today about two variable absolute value graphs, which are also called V-shaped graphs. So goal is to be able to graph two variable absolute values. Why absolute value graphs are a good way to show distance over time from an object that passes another object. It's a really good application. Also, we're going to talk a lot about transformations today, and that's going to get us really ready to start graphing parabolas when we get to our unit on quadratics. Okay, so what does it mean to shift a graph? So this is a technique for graphing where we can graph like a simpler function and then shift it to where it needs to go. And so what does it mean to shift a graph? It's to take every single ordered pair and move it in the same direction, the same number of units. So here we can see that our red line is being shifted 2 units to the left, and every single point is moving those same 2 units. All right, next question. What type of shift do we see here? In red, we have y equals sine of x. Well, this one has been shifted vertically. So on the previous slide, we saw a horizontal shift. Now this is vertical shift. Every single point has been moved 2 units up. Here's one other type of shift that can happen. Going from the blue to the red this time, we have this parabola in blue. And then this one has been vertically flipped. All right, so our 3 types of shifts are horizontal shifts, vertical shifts, and vertical flips. Horizontal flips are also possible, but a lot of our graphs are symmetrical horizontally, at least absolute values and parabolas, so those don't really change the shape at all. All right, now I want to change gears a little bit and sketch this scenario just sort of conceptually. So you're walking at a rate of 50 yards per minute. You're 200 yards away from the state border. You walk past the border and keep going. We want to graph our distance from the border over time. So naturally time would be on the x-axis. And let's just see. If I'm going 50 yards per minute, I'm 200 yards away. It's going to take me 4 minutes to get there. So let's go out to at least 8 minutes here. Have tick marks for every minute. Also, we should say time, but then specify that this is in minutes. All right. And then for our y-axis, this is our dependent variable. So how far we have walked depends on how long we've been walking. So, and we start 200 yards away, so we better make sure we go up to at least 200. So I'll just put 200 right there. And then tick marks at 100, 50s, maybe 25s. All right, so then we should have this distance in yards. All right, so at 0 minutes, I'm still 200 yards away. And I'm going 50 meters per minute, or yards per minute, towards the border. So after 1 minute, I'm 150. After 2 minutes, I am 100 away. After 3, I am 50, and then at 4 minutes, I reach the border exactly. But this line does not continue going down at this point. All right, at this point here, as I walk past the border and continue on in a straight line, my distance from the border actually starts going back up again. So it went down until I crossed it, and once I cross it, it starts going back up again. So 1 minute later, now I'm 50 yards away from the border. 2 minutes later, I'm now 100 yards away. I'm on the other side, but we're just doing the absolute distance, which is only a positive number. And so we can see that this graph bounces and starts going back up and creates this V shape. This is an absolute value graph. All right, let's save this for now. We'll come back and write an equation for this in just a second. All right, so first, as we get more into graphing absolute values, we need to be able to talk about their different features. So the point at which the absolute value bounces, the tip of the V, that is called the vertex. All right, and this graph right here, where the vertex is at 0, 0, this is probably the graph y equals the absolute value of x. We call this our parent function because it hasn't been shifted in any way. All right, right through the vertex, we can add in a dotted line that's vertical, and then label this our axis of symmetry. The axis of symmetry. All right, and we'll just label this our parent function. So one idea for graphing these is to always start with this graph here with the vertex at 0, 0, and a slope of 1 and -1 on both sides. To start with this graph and then just transform it wherever we need it to go. So what do we call this type of transformation? Compare it to the previous graph and we'll see that this has gone 2 up, so this is a vertical shift. And the letter we're going to start using for this is K. All right, here the vertex has been moved 2 units to the right. This is going to be called a horizontal shift. The variable we're going to start using for this is H. Okay. I feel like we're still missing a piece here. Let's write out the generic form of a 2-variable absolute value equation. Y equals A times the absolute value of x minus h plus k. K here is going to be our vertical shift. H is going to be the horizontal shift. And then A has a lot of different roles within the function. This controls vertical stretch and vertical flips. So if it's like a number bigger than 1, it's going to stretch it out. If it's less than 1, it's going to vertically compress it. And if it's negative, it's going to vertically flip it. Okay, now I think we're ready to graph the one on the next slide. So graph y equals the absolute value of x minus 2 plus 3. So I'm just going to dot in our parent function real quick onto this graph. Not going to connect the dots. I'm only going to connect the dots once I've got my final graph. But here is the equation y equals the absolute value of x. Now we're going to shift it to a different spot on the plane. So all of those points are going to move 2 units right and 3 units up. And this is a little bit tricky that it's to the right because you see a minus and you think, well, shouldn't minus be to the left? That makes more sense. But it's because the formula already has that minus built in. It's x minus h. that this still moves us to the right. So just kind of remember that this one's backwards of what you might think. And now let's move all of these points, and I actually just focus on just the vertex, moving it 2 right and 3 up. And then as long as I haven't stretched anything, done a vertical stretch or a vertical flip, then I can just keep a slope of -1 and 1 on either side of this vertex. So there is our graph for y equals the absolute value of x minus 2 plus 3. It's been moved to the right and 3 up, and it still is this V-shaped graph. All right, now let's graph y equals -2x plus 4. So this one has been moved up 4. And that's the only transformation on the vertex. So the vertex was at 0, 0. Now it's at 0, 4. And then this, here's kind of a trick for you. This is the slope going to the right of the vertex. So I go to my vertex, the slope is -2 going to the right, so I can get my next point, the point after that, all of these points. And then all you have to remember to do is just make this symmetrical. Because these V-shaped graphs, now this is an upside down V, so it's more like a mountain, but they're always symmetrical. So I just make it symmetrical over its axis of symmetry. I get this side over here, it has a slope of +2. Hits the vertex there at 0, 4, bounces back down. And there's our graph. All right. That is the end there. I feel like we could just use one more example to really make this clear. So y equals 3 times the absolute value of x minus 1 plus 4. How I graph this, here's my super quick method for graphing. All right, I look at this value here and this value here to get the vertex, which always flip the sign on that first one. So although we see a -1, it's a +1, 4. So 1, 4. Then I look here to get the slope going to the right, and then I make it symmetrical. And that is my super quick way of graphing these V-shaped graphs. All right, I'll put in a couple questions for you here. Other than that, have a good rest of your day.